All right, now we're going to look at a really famous result and really pretty useful and interesting. It's called Bayes' theorem, and it's a way that we kind of reverse the conditions in a conditional probability, kind of almost reverse the sequence of events. So with conditional probability, if we know something has already happened, like in sequence, right? This thing has already happened, and then we find the probability that something else might happen. With Bayes' theorem, what we do is we try to reverse the cause and effect part, where we say, okay, if I learned the effect, if I learned what happened after, what's the probability that this other thing would have happened before that? And so with Bayes' theorem, what we're doing is taking that conditional probability definition. So for example, we know that by definition, probability of A given B is equal to probability of the intersection divided by the probability of B, right? The condition here, the event B, is our new universe. But if I just sort of reverse the roles of those events, the probability of B given A over here is the probability of their intersection divided by the probability of A, because in this case I'm kind of making A the new smaller sample space. Now this gives us two ways, I mean it's really the same kind of way, but like two different seeming formulas for finding the probability of A intersect B. So let's say if we take the probability of B given A, which is equal to P of A intersect B divided by P of A. If I multiply both sides by P of A, we get the probability of A intersect B equal to P of A times P of B given A, right? That product right there. On the other hand, if I take this form of the conditional probability and multiply both sides by the probability of B, we get that P of A intersect B is equal to P of B times the probability of A given B. Now both of these formulas give us the probability of A intersect B. So now on this line, that's where this comes from. This way to find A intersect B gives us this side. This way of finding A intersect B gives us this side. They're both equal to the probability of A intersect B, which means they must both be equal to each other. So the far left and the far right sides of that equation are equal. Now let's take this and we will divide both sides of this equation, or I guess you could think of it as all three sides of this equation, by P of A. But we're really just going to be interested in this side and this side, right? Those are equal to each other. On the very left side, the P of A cancels, and we have the probability of B given A is equal to this fraction over here, right? And that gives us this equation. This is the basic statement of Bayes' theorem right here. So it says that the probability of B given A is equal to, you take the probability of A given B divided by times the probability of B and divided by the probability of A. It's a way that we can find the probability of B given A if I know the conditional probability going the other way. And then of course I also need to know the probability of B and the probability of A. So this is the basic statement of Bayes' theorem when we're talking about two events. You can extend it to allow for more events that are disjoint, and the idea is that I have a certain number of events, let's say n disjoint events, that partition the sample space, right? So I know that one of those things will happen, and they're not going to both happen, or not more than one of those things will happen. Then the probability of BI, given that A has occurred, if we know that A has occurred, then we find this conditional probability by taking, the top looks the way it should. The probability of A given that BI has occurred times the probability of BI. So far, that looks just like we see up here, okay? The bottom looks a little bit different. So when we looked at it in two spaces and with when we looked at it with just two events, on the bottom we have just P of A. Now we have all this sum, right, of all these products. So what we're doing here in the bottom is that we are partitioning A. If we partition A, the event A, into these disjoint sets or events, which is A intersect B1 union with A intersect B2. Remember, the BIs are disjoint, right? They're a partition for the sample space. So A can only intersect one of them at a time. So these intersections are disjoint. So I'm kind of partitioning A into the event that A happened with B1 happening, or A happened with B2 happening, or on down the line. And each of these, like let's say I just take a look at the first one, that's an intersection. So the probability of A intersect B1, we know, is the probability of A given that B1 occurred times the probability of B1. And that gives us this first one, right? And then we just do the same thing with all of them. Now this formula that we have in the theorem looks a little bit complicated, but there's a pretty intuitive way to actually execute this formula that doesn't even really require us to kind of write it out in this fashion. So let's do an example. Let's sort of see it in action, and I think that's sort of the easiest way to understand Bayes' theorem. So we're going to suppose that Sam goes out to buy a garage door closer, and there are 3 different garage stores that sell these garage door closers. He can go to Andy's. The probability that he goes to Andy's is 0.3. He might go to Ben's, and the probability goes to Ben's is 0.2. Or he might go to Charlie's, and the probability that he goes to Charlie's is 0.5. Now he's going to go to precisely one of these. He's not going to go to more than one. Note that these probabilities all add up to 1. So he's going to go to one of these stores. And if he goes to Andy's, we have these different probabilities. If he goes to Andy's, there's a 0.2 probability that he'll make a purchase. Maybe Andy's has crappy doors. If he goes to Ben's, the probability he makes a purchase is 0.4, and if he goes to Charlie's, the probability he makes a purchase is 0.3. So note the sequence of events. If Sam's getting ready to leave the door, right, to walk out of his house, the first thing he's going to do is decide which place to go to, right? So in the actual chronological sequence of events that happens, we have a starting point. I'm going to make a little probability tree, and this is how we're going to find kind of useful to organize our work. So he's either going to go to Andy's or Ben's or Charlie's. When I make this tree, I really have to start with what comes first chronologically. So he's going to pick a place to go. Andy's, Ben's, Charlie's. And on the branches, I'm going to put the probability. So there's a 0.3 chance he goes to Andy's, there's a 0.2 chance he goes to Ben's, and there's a 0.5 chance he goes to Charlie's. Once he goes to one of these stores, he's either going to buy a garage door closer or he's not, right? So that's what happens in the next sequence of things, chronologically. He buys or doesn't buy. On these branches, we're going to put the conditional probabilities. So if he goes to Andy's, the probability he makes a purchase is 0.2. And that's because this is the probability, this is the conditional probability that he buys given that he goes to Andy's. Right, that's the information that they gave us here. So the information given in these 3 bullets, these are conditional. Right? If he goes to Ben's, if he goes to Andy's, if he goes to Charlie's, those are conditions. So there's a 0.2 chance he'll buy if he goes to Andy's. That means there's a 0.8 chance he doesn't buy. If he goes to Ben's, there's a 0.4 chance he'll buy. And that means there's a 0.6 chance he does not. And if he goes to Charlie's, there's a 0.3 chance he buys and a 0.7 chance that he does not buy. So we're just kind of laying out, organizing the information they gave us. But what gets interesting now is the question. If he does in fact buy a garage door closer, what is the probability he bought it at Ben's? So we're reversing the chronology here. We're saying, suppose I know at the end of the day he comes back with a garage door closer. What's the probability that he went to Ben's? So note that picking the store you go to, that happens first chronologically, and then he decides whether to buy or not. So I'm saying if I know the outcome, if I know that he buys, what's the probability that he ended up going to Ben's? So we want the probability that he went to Ben's, given that we know that he bought a garage door closer. Now I can think of this Bayes theorem just by how we define the conditional probability as being the probability of the intersection. He went to Ben's and he bought a garage door closer, divided by the probability that he bought a garage door closer. So the probability that he went to Ben's and bought a garage door closer is represented by taking this path on the probability tree. He went to Ben's and he bought the garage door closer. So we know that the probability he went to Ben's and that he buys, we're going to take the probability he went to Ben's and multiply it by the probability that he bought a garage door closer given that he went to Ben's. I'm going to multiply those two values. When we make a probability tree like this and we put the conditional probabilities on these secondary branches, this builds in, this has built into it the probability rules, right? So this is the probability that he went to Ben's times the probability that he buys given that he went to Ben's, right? This is how we find the probability of an intersection. So this is 0.08. That's the value that's going to go down here on top. Now we need to know what's the probability that he actually just bought a garage door closer from anywhere. So if he bought a garage door closer, that means he did so either by going to Andy's or Ben's or Charlie's. That means we're trying to find what's the probability that he went down one of these paths, one of these three paths in the tree. Each one of these paths, we're going to find the same way that we found this last one. So up top, that's the probability that he went to Andy's and bought a garage door closer. So that's 0.3 times 0.2. And that's 0.06. At the bottom here, we have the probability he went to Charlie's and bought a garage door closer. And that gives us 0.15. Now we know that one of these happens, right? If we know that he bought a garage door closer, he did so by traveling down one of these three branches that's highlighted in red. And these three branches, they're mutually exclusive. He did travel down precisely one of these branches. They're mutually exclusive, which means the probability that he bought a garage door closer is the sum of these probabilities. If you add these up, we get 0.29 in the bottom, and doing some division, you get 0.276 approximately. So if Sam bought a garage door closer, there's a 27.6% chance that he went to Ben's. Okay. So now, suppose there's a special case where these events, these B sub i's, that we use to partition the sample space, if they're all equally likely, then Bayes' theorem simplifies a little bit. You can see the bottom looks a little bit different. They're no longer products that we're adding, but just the individual conditional probabilities that we're adding up. You can still approach each problem the way we did with the probability tree, and to be honest, that's usually how I do it. If we have 3 urns, suppose we've got 3 urns, urn 1 contains 3 red, 4 blue, and 6 white marbles. Urn 2 contains 5 red, 3 blue, and 2 white marbles, and the third urn contains 4 red, 2 blue, and 4 white marbles. So these 3 urns contain different numbers of the same color marbles, right? So they all have red, blue, and white marbles, but just in different numbers. So what we do in this experiment is first we select an urn, and then we draw a marble out of it. So we're randomly selecting an urn. So in the beginning, these are all equally likely. So I'm either going to take urn 1, or pick urn 2, or I'll pick urn 3. So they're equally likely, so I've got a one-third chance each time. Now, depending on how they ask the question will determine how I choose to set up my branches. I could set up, blue, red, white branches on each urn, and that would be fine. But if we look at the question they're asking, we might be able to set up a simpler one. They say that an urn is selected randomly and a marble is drawn from the urn. So after we select the urn, then we pick a marble out of it. If a red marble is selected, what's the probability that urn 1 was chosen? Okay, so we're only considering the possibility where we draw a red marble. So instead of making 3 branches out of each urn for each color, I'm just going to make 2 branches for red and not red. Urn 1 contains 3 red marbles. So there's red, which is, 3 red, 4 blue, and 6 white. That's 13 total, so that's 3 out of 13 probability of drawing a red, which leaves us with not drawing a red probability of 10 out of 13. Urn 2 contains 5 red, 3 blue, 2 white marbles, so that's also 10 marbles. 5 of them are red, so we have a 5 out of 10 chance of getting a red, which is 5 out of 10 chance of not getting a red. And then the third urn has 4 red, 2 blue, 4 white. So that's still 10 marbles. 4 of them are red. That means 6 of them are not red. Okay. So what we want is, if a red marble is selected, so if I know that the condition is that a red marble is selected, what's the probability that we chose urn 1? So what we want is the probability that we chose urn 1 given that we selected a red marble. We know that this is the probability of their intersection divided by the probability of getting a red marble, right? That's our smaller sample space, the universe in which the marble we draw is red. Okay, so in this universe, we know we drew a red marble, right? So that means we went down this branch, or this branch, or this branch. We can find the probabilities that we went down each of these branches by multiplying the probabilities along those branches. So the probability that we chose urn 1 and got a red marble is 1 out of 3 times 3 out of 13, which is 1 out of 13. The probability that we chose earn 2 and got a red marble out of it is 1 out of 3 times 5 out of 10, or I guess 1/2, and that's 1 out of 6. Next, the probability that we chose earn 3 and got a red marble out of it is 1 out of 3 times the probability 4 out of 10, or I guess 2 out of 5, and that's 2 out of 15. These together tell us the probability that we drew a red marble. So that's the bottom. Now the top is the probability that I picked earn 1 and drew a red marble, and that's just one of these. That is this 1 out of 13. So that's what goes on top. So 1 out of 13 divided by 49 over 130, which means this is 1 out of 13 times 130 over 49. We can do some canceling. So we get 10 out of 49, which is approximately 0.204. That is the probability that we selected earn 1 in the first place if we know that we got a red marble. I'd like us to just point out, I'd like us to observe right now that the probability of selecting earn 1, if we didn't know anything about the overall outcome, about which marble, you know, there's a 1 out of 3 chance of selecting earn 1, but as soon as I know what the outcome is, that goes back, that changes the probability that I selected earn 1 in the first place if I know I got a red marble. It actually decreases it a little bit.